Hello everyone, in this video we will learn about the theorems on tangents to a circle. But before learning about the theorems, we must learn about the position of a line about a circle. Position of a line about a circle. Suppose we have a circle here with center O. Then we can draw three different lines here. One is this line AB, which is not intersecting the circle at any point. Another may be the line which is intersecting this at one point P. Suppose this line is XY. And the third line we can draw here, this is suppose MN, which is intersecting this at the point C and D. What are these lines? What are the three positions we can have? Number one, we can have a line which lies completely outside the circle, like AB here. It is not intersecting at any point. It does not intersect the circle at any point. Second is the line XY, which is intersecting at only one point P. A line XY which intersects the circle at only one point, that is P here we have taken. This is known as the tangent to the circle. And the third line is MN, a line MN intersecting the circle at 2 points. Such line is known as the secant of the circle. So we have three different lines. One is lying completely outside the circle. Second is which is intersecting at only one point, known as the tangent to the circle. And the third is which is intersecting at two different points, is known as the secant to the circle. It means we can define the tangent to a circle as a line which intersects a circle at only one point, or we can say touches the circle, is a tangent to the circle. What is the point of contact? The point at which the tangent touches or intersects the circle is called the point of contact. Say if we have a circle with center O and xy is the tangent touching at point P, then this point P is known as the point of contact. The first theorem we have is a tangent to a circle is perpendicular to the radius through the point of contact. We know that we have 4 steps to be taken to prove any of the theorem. So here also we have those 4 steps. They are: number 1 given, number 2 to prove, number 3 the construction, and the 4th one is the proof, main part of the proof. So here we first draw the diagram. The diagram is, suppose this is a circle with center O and there is a tangent drawn to it xy which is meeting or intersecting this at point P. So P is the point of contact and there is a radius through P, that is OP. We have to prove that OP is perpendicular to xy. So what is given to us here? A circle COR. The meaning of this is the circle with center O and radius R. XY is a tangent intersecting at P. OP is the radius through P. This is what we have been given. Now what is to be proved? To prove OP is perpendicular to XY. This is what we have to prove. Construction. If any construction is required, we write in this particular part. So the construction is, take a point Q on XY other than P and join OQ. Then we will go to the proof. We know that the shortest distance to a line from a point is perpendicular to the line. The same thing we will apply here. So we say here Q is a point which is outside the circle. So we can write, since Q lies outside the circle, therefore OQ is greater than the radius. It means OQ is greater than OP. It means OP is less than OQ. It means we take any point other than P on this line XY, the line joining to that point will be greater than this OP. It means OP is the shortest line drawn from O to XY. Therefore, OP is the shortest line of all the lines drawn from O to XY, and this implies that OP is perpendicular to XY. Other way we can do it, that we can write a point here where OQ is meeting this, suppose this point is R. Then we can write OQ is equal to OR plus RQ. And OR is the radius, OP is also the radius. So we can say this is equal to OP plus RQ. This implies that OP is less than OQ. And then we can write the same thing here and we can prove that OP is perpendicular to XY, hence proved. This is the way we can prove this particular theorem. If we draw tangents to a circle from an external point, at the most two tangents can be drawn. And the next theorem is based on that only, that the lengths of two tangents drawn from an external point to a circle are equal. To prove this, first we draw a diagram. This is a circle with center O and there is an external point P from which we draw a pair of tangents to this particular circle. PA and PB are these two tangents. We have to show that both the tangents are equal in length. To prove this, what we write, given the first point, a circle COR, center O and radius R. PA and PB are two tangents drawn to it from P. To prove PA is equal to PB, the length of both the tangents are equal. Now we go to the construction. Construction is join OA, OB and OP. So we join here OA, OB and OP. Now we go to the proof. We know that according to the first theorem which we have learnt, tangent is perpendicular to the radius at the point of contact. So we write here, we know that tangent is perpendicular to the radius at point of contact. Therefore, angle A is equal to angle B is equal to 90 degree. So this angle is 90 degree and this angle is also 90 degree. Now if we go in these two triangles OAP and OBP, in triangles OAP and triangle OBP, just now we've seen that angle A is equal to angle B is equal to 90 degree. We have already proved it. OA is equal to OB because that are the radii of the circle, and OP is equal to OP, which is the common side to both. Therefore, triangle OAP is congruent to triangle OBP. By what? By RHS congruence, by RHS congruence. And if they are congruent, certainly the corresponding parts of that will be equal. So we can say PA is equal to PB. This implies PA is equal to PB by what? By CP, CT, that is corresponding parts of congruent triangles. And this is the proof of this particular theorem. From the same concept, we can prove some more points here. Like in this particular figure, we have proved that triangle OAP is congruent to triangle OBP by RHS congruence. Therefore, can we say that this angle 1 will be equal to angle 2 or not? So we can say angle 1 is equal to angle 2 by CPCT, that is by corresponding parts of congruent triangles. It means what? This shows that line OP bisects the angle APB in two equal parts. So we can say OP bisects angle APB, that is the angle of intersection of the tangents. So this can be learnt as a theorem that if we draw a pair of tangents from an external point to a circle, the line joining the point to the center of the circle bisects the angle of intersection of the tangents. Next point, we can also say that this angle is also equal to this angle. Suppose this is 3 and this is 4. We can also say that angle 3 is equal to angle 4. That is also by CPCT. It means what? We can say that OP bisects angle AOB. It means we can remember this also as a theorem that the line joining the external point to the center of the circle bisects the angle subtended by the tangents at the center. Next, one more thing we can learn here. In quadrilateral AOBP, do we find that angle A plus angle O plus angle B plus angle P is 360 degree? That is angle sum property of quadrilateral. In this we know that angle A is 90 degree plus angle O plus angle B is also 90 degree plus angle P is equal to 360. So can we say here that angle O plus angle P is equal to 360 minus 90 minus 90, that is 180 degree. It means what we can say that angle AOB and angle APB are supplementary. So one more theorem we can learn here, that the angle between the tangents and angle subtended at the center are supplementary to each other. We can say one more thing here, that angle A plus angle B is 180 degree. Also angle O plus angle P is 180 degree, and if opposite angles of a quadrilateral are supplementary, can we say then this is a cyclic quadrilateral? It means we can say therefore AOBP is a cyclic quadrilateral. So like this, many of the theorems can be taken based on tangents and proved. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.